Hello, welcome back. This will be day 4. Um, yeah, let's just get right into it. Okay, so this is day 4. This basically looks like okay. So we're gonna generate numbers in some range, and then we're gonna evaluate a bunch of actually just the two conditionals. Two adjacent digits are the same. Going from left and right, the digits never decrease. Okay, we can do this. So let's copy our puzzle input. No parsing this time. Let's go ahead and get our solution file open. Yes. There we go. All right, so in order to evaluate, these conditionals, what I'm thinking is we basically decode the number into a list, and then we can do pairwise reduce to look at this, and we can do like a Boolean expansion to evaluate this. And then we can reduce them. And yeah. Okay, so two adjacent digits are the same. All right, so if we are going to start decoding, if we know that the digits are 6 digits long, then we can just do 6 row 10 W, something like this. And then if we have a 6-digit number, oh, right, reverse that. Let me get something like this. So decode in APL is, at least in Dyalog, is a little bit weird. You have to specify the exact number of like placeholder digits that you want to decode into. I think in Dyalog Extended, that atom from Dyalog is put together. There's an operator where you can just specify the base and it'll sort of automatically expand. But for standard, this is what we've got. And then we can assign this to D for decode. And what's the first conditional? Two adjacent digits are the same. Yeah, sure. So this will be 2 equals reduce. Pretty sure. Yep, so we get a 1 there in the middle because 3 and 3 are the same. And then we'll do an or reduce, because any one of them being true would be fine. Yep. And we will do that. And what's the other one? The digits never decrease. The digits never decrease. They only ever increase or stay the same. Yeah, so actually we can do comma never decrease. So that means that each left digit is going to be less than or equal to, yep, and then we'll do and reduce. Yeah. Okay, so if we just do, let me just tell you about this Boolean expansion here. Oh, geez, yeah, right. I have to apply this on the decoded version. Like this. So we can see Oh, that's not going to work. Yeah. The digits never decrease. Okay, I guess we can do something like, we can do another piecewise reduction here, like this. Yeah, and then we can and reduce it. Okay, fine. So we'll do this against D2, and then we'll and reduce the whole thing. Okay, let's just, the following are true. So 1, 1, 1. Yep. I notice that we don't have any negative test cases here, but we'll at least, does not, oh, no, we do. Does not meet these criteria. Sorry. A little all over the place. Yeah, that is true, or not true. And this one should also fail, and it does. All right, cool. So we will name this as F. We'll just go ahead and put that over in our solution. All right, and then the next thing that we have to do is we have to figure out how we're going to generate a range from two numbers inclusive. So let's just imagine that we have a function that takes two arguments. It'll take alpha being the number that we want to start from and omega being the number that we end on. So I think that we'll want to do something like W minus alpha iota alpha plus, and I probably have to adjust these ranges somehow. So let's just test this. If we want to generate from like 10 to 20. The problem is that we're missing the 10. And I think this range is inclusive. Within the range, it's sort of ambiguous, but let's assume that they mean inclusive. So actually we'll have to do, because we want to generate one more number, we'll have to do 1 plus here, and then we'll have to subtract 1 from the whole thing. Like this. Yeah. All right, cool. So let's call this range, R for range. And we might be able to simplify this. Let's put these both on one line as sort of helper functions. And then our question is, your puzzle input, how many different passwords within the range given in your puzzle input meet these criteria? So basically, if I put our range function in between the elements in P, how large is that? Apparently none, which is odd. Oh, because it's right. Oh, that's a little bit weird. Why is that enclosed? Huh. All right. Well, and how big is it? 475, 765, and minus reduce P like this. Fine. Yeah, that seems right. That seems right. So the number of elements in our range, if we're taking the inclusive range, should be one larger than the difference. Cool. All right, so we have this, and then we want to do for each f, and that should give us a Boolean array, and we can add them to find out how many are true. 1640. Yeah, well, let's try it. Sweet. All right, so before we continue, we'll just put this over here as part 1. This is a little bit, I mean, I don't know. APL may not really shine when you're just like evaluating a bunch of conditionals, but still this is kind of cool. We're operating on some Boolean arrays at least. What's part 2? The 2 adjacent matching digits are not part of a larger group of matching digits. Oh, okay, all right. Okay. It's not part of a larger group of 4, 4, 4, 4. Uh-huh. Okay, so what does this mean? This basically means okay, so 1, 2, 3, 4, 4, 4 no longer meets the criteria, right? So let's just take this one. All right, now before we were doing a 2-element equality reduce. Rank error. Yeah, okay, yeah, sure. So we'll take this. We just want the decode. We're basically just doing this, right? And it's 1, 2, 3, 4, 4, 4. Uh-huh, yep. But the problem is that we have 2. Okay, here's what this looks like if we just do an enclose, so you can see sort of, okay. Yeah, like this. So when we do a 2-element comparison, there's going to be 2 checks that are next to each other that share the same element. So if we have 2 elements that are next to each other, if you have 2 elements that are next to each other, then that would indicate that, you know, that it wouldn't pass. So one way we could do this, there's probably a more efficient way, but let's just go with this. We can use the find operator, or the find function. Find will tell you if an array occurs in another array. So we can do it like this. So if we go down and we do, so we know with the equality operator we'll get 0, 0, 0, 1, 1, right? And we're basically asking, does 1, 1 occur in that? Yeah, and we would or reduce to get 1. So let's look at F. So okay, so if we say that this is equality reduce, let's call this E, I guess, for equality. We're gonna or reduce it, so that should be, so there should at least be 1, 1 in there, right? But what we don't want to be true is we don't want 1, 1 in E. We can do or reduce not, like this. And if we do this to 1, 2, 3, 4, 4, 4, we should get 0. Right? Let's try some other test cases. So this one should still be good. Because the digits number decrease and all repeated digits are exactly 2 digits long. Okay, so that did not work. Fair enough. Let's see what we get for this. Uh-huh. Oh, this should be, we should concatenate this. Yeah. Okay, sorry. Okay, great. So 1, 1, 2, 2, 3, 3 is fine. This one should still, so this is 1, 2, 3, 4, 4, 4. That should be 0. And oh, that's interesting. Yeah, this will fail. So it's not the fact that there is 1. All right. Huh. Very interesting. Okay, so what we want to do here, let me think. Let me look at these two Boolean vectors. I have an idea. So I have 1, 1, 1, 0, 1, right? And if I say 1, 1 in this thing, we get 1, 1, 0, 0, 0. So, this is tricky. Oh. All right, I have a crazy idea. This is not going to be very efficient at all. But I think it'll work. Okay, check this out. We are going to use the stencil operator. I know, it's nuts. And we're going to say, if this works, I'll explain what the stencil operator does. But so right now we're going to take elements of 3, and let's just, for right now, let's say that we're just going to enclose omega. Uh-huh. And basically what I want is 0, 1, 0 match omega. Yep, and then I want to do an or reduce 1. Uh-huh. Okay, so let's try. Let me just see if this works. So I'm going to take this, and then we can avoid all of this nonsense. Yes. Yeah, very good. Okay, let's try our test cases against this. 1, 1, 2, 2, 3, 3, it's fine. That's 1. This no longer meets the criteria. Uh-huh. This one does meet the criteria. Yep. All right, well, so let's say that this is our function. And well, we'll have to call this, because this is for part 2, we'll have to call this different. So let's call this G. And then we will say the same thing. So we're saying G for each G. This is going to take longer. Oh yeah, it is. The stencil operator is not efficient. But, you know, 1126. So this should be strictly less than what our answer was before. And it is. Yeah. Okay. So I don't feel good about this solution. Geez. Okay, well, just for fun, let me tell you what the stencil operator does. So the stencil operator, basically, it's most often used on, let's say, like, it's most often used on a 2-dimensional matrix, but it'll work on a 1-dimensional one as well. And what it does is it basically iterates, it steps through each element, and the amount that it steps on each iteration can be controlled. I forget the exact, there's some documentation on this that tells you how to control the step function, but basically you're saying, okay, take a 3x3 window, step through this, and sort of partition the matrix in each way. And what makes it useful for our case is that it pads the area outside the bounds with the zeros. Right. So, and yeah, you can change this. I think you can do like 4, 4 here. Yeah. But what it does, say like we did this for 3 on iota 5. Right. So we get a 0 on the left side because it's kind of padding this out. So it has to take a 3-wide window starting at the first element. So it pads it out with 0. It'll take a 3-wide element on the last element and also pad it out with 0. So this makes it quite useful for our Boolean matrix here, because we had something like this, right? So we have this guy, and if we apply this over here, what we're really interested in when we do our equality test is we want the 1 to be isolated. And it's isolated if it has zeros on either side. But the trick with doing this is that you would have to take the edges into account. But stencil will do it for you because it fills with zeros. Now, all that being said, let me see if I can figure out a more efficient way to do this. Well, let's get down what we have so far. Yeah, so this is now G. right? And this is it's a little bit ugly. And we'll say this will be part 2, except that we are using G. Okay. So we want a single group. We want a single. You know what? Okay, if we take a number like this, we sort of do iota roundabout, like, oh my goodness. I'm just going to separate out this decode function because it'll be nice to have. So, yeah, let's call this like S. And, yeah, like this. Yeah. Sorry. Okay, so we have 1155. 111155. Okay, if we switch this around and we say like this, 33. 121212. Yeah. I'm thinking of using like the key operator to try and count groups. What if we did something like iota dot length equals. This is commonly used to like find duplicates. Yeah, that's not going to be helpful. Geez, I don't really have any good ideas. There's some very clever things that people can do with like Boolean arrays. I'm sure someone will come up with a clever solution for this, but it's kind of yeah. What if we do equal expand? Right, so we do equal expand like this. Yeah. And what was the one that we wanted to test? 11122. Yeah, I'm still going to want to test for like an isolated group here. It's all kind of it's kind of gross. How would I do this in an imperative language? I would loop through, I'd keep a variable, I'd keep like a count. Can we partition somehow? Maybe. So if we do like S this thing, geez. What the hell is S? Oh yeah. We're able to partition somehow. Pick and close. Huh. I really want to split it into equal groups. There is a clever way to do this. Okay. Nothing really comes to mind. Depth, tally. Yeah, all right. Well, I'm going to roll with this for right now then. But we can clean it up quite a bit. So we can basically say, yeah, we're doing this function right here, this kind of piecewise equality. Does that work? Well, we can certainly hang on one second. Okay. So let's see. Yeah, we can specify our S function, this thing. We can split that out. Right? And then we're basically saying then we're basically saying like f.s, right? Like this. This will be g.s. This can just become w. That is also w. I'd like to factor this out somehow. Let's just make sure that this works. It does. Okay, cool. Oh, it's got to finish evaluating before I can modify text. That's fine. Yeah, and then we can just put this in line here, and then this up here will just be helper functions. So you have R and S. Same with G. You can put that in line over here, like so. Man, there's a lot of similar functionality. Hmm. Uh, 2 less than W. Yeah, let's say I'll figure out a way to reduce this, I'm sure. Well, this is what I've got for right now. At least, hey, at the very least, I got a creative use of the stencil function. And I think that the stencil is a pretty cool APL function. I think it's useful. I think it was useful in a couple of the previous admin of code challenges. So hopefully we'll get the opportunity to use it on a matrix at some point in the future. But yeah, thanks for tuning in. Hopefully, hopefully this was helpful. And we will see you next time.